Good morning, everybody. Thank you so much. Thank you so much for sparing your time, valuable time, to attend this course. And I'm really grateful to Dr. Jasprit, Dr. Rajiv, and other faculty members who have helped us to organize this course. And we are also grateful to Human Resources of India, providing us financial resources to conduct this course. So the meaning of this course is to give you some light, or to explain some of the recent advances in the field of material science. Can you hear me up to the last one? Okay, okay.
You can come forward if you have some.
Yeah.
The last 10 students, they can come forward. We have set.
So, yeah. I have planned this course through the series of lectures. Before arriving at the material chemistry or the applications of the material chemistry in terms of magnetic nanoparticle, we will begin with some of the fundamental aspects which are required in order to understand the course material. So, what we will be doing, today's lecture is slightly rigorous lecture. I have to cover 27 slides, I think, in just probably I have less than 50 minutes. So I'll be speeding up, and this whole lecture is focused on the fundamental of solution chemistry, because the solution chemistry is the most important branch in chemistry to understand how we can synthesize nanomaterial in the solution phase. Okay, so it's a quantification of solute-solvent interaction. When we have to synthesize any kind of nanomaterial, whether that could be gold nanoparticle, silver nanoparticle, with whom you are quite familiar with, and most of you are synthesizing them, it all starts with the solute-solvent interaction. It's a basic solution chemistry. So we know that when we have to deal with the solution chemistry, so we deal with the homogeneous solutions, and these are the fundamental aspects which we need to understand quantitatively, that is molarity and molality, apart from mass percent, ppm or ppb. But in this lecture, and particularly throughout this course, we will focus our attention on molarity, molality, and mole fraction. I don't need to explain it in that depth, but I will help you to recollect some of the fundamental aspects of these definitions. Then we have to understand the molarity and molality. In chemistry, it is very important because it's a quantitative science. Chemistry is a quantitative science. So when we understand our definition, we go through a definition or a concept. We need to understand that how we can apply this concept quantitatively. Quantitative means that we need to arrive at some kind of numbers on the basis of which we can say that this property is going to be enhanced or reduced. So quantitative is we can measure that property quantitatively. So when we have to deal with these definitions, you have to keep in mind that the units are very, very important. If you can understand the units, you can understand the definition. Suppose if I say that how we can define the molarity. So molarity is basically moles of the solute. You can write mole with MOL or MOLE, both are correct terms, and divided by the volume of solution. It is not the solvent, it is the solution. Solution means solute plus the solvent. On the contrary, when we deal with molality, so molality, the only difference is again moles divided by the mass of solvent. Now, the most important thing is, you know, the definition of the mole. So when we have to write or understand the definition of the mole, it is the solute, mass of the solute divided by the formula mass. right? And if I'm going to place in both cases, so it is mass divided by formula mass, and here it is volume, and here it is the same way if I'm bringing over there, so it is the mass. But in order to arrive at the units, you know that molarity is molar. Molar is a short form for mole per L, right? On the other hand, molarity is, it is mole per kilogram. Now how can we arrive at the units of mole per L? So what we will be doing actually, so it is mass in grams. Gram per mole is the units of the formula mass, and the volume here you will be taking because it is L, not ml. So therefore volume must be taken in L. If you are going to solve it, eventually it is mole per L. The same way over there, so if you are evaluating the units for mole per kg, right, and it is gram per mole divided by kilogram, and the same way you will be coming mole per kg. Now, the question is, the obvious question is, why we need to have two different definitions, right? So why can't we deal with the molarity only, or the molality, and why we need to explain the two terms for the concentration of the solute in the solvent? The question is, it's altogether related to the fact that when we deal with the volume, I mean to say, here it is the volume, it is temperature dependent. So volume is temperature dependent. Whereas when we deal with the mass, so then we can exclude the temperature dependence term. So in other words, what is the meaning for this? The meaning for this is when you have to measure, or you have to deal with the experiments where you have to vary the temperature, it means that it is not advisable to use the concentration in molar units. Then you will be using the molality rather than molarity. But when you are dealing with a constant temperature, so then molarity is good enough in comparison to that of molality. It is much easier to measure the volume in comparison to the weight of the solute of the solvent. So therefore, the volume of the solvent, when we are measuring in the volume of the solution we are going to measuring, so it is much easier in the case of molarity, and hence at constant temperature we can easily apply the definition of molarity in comparison to molality. This is the most important aspect that you have to keep in consideration. The reason is any kind of nanomaterial synthesis, so you have to prepare the solutions where you will be dissolving either the gold salt or the silver salt. So I mean to say that you must be very careful in terms of the concentration, which concentration units you are going to apply. So this is what I have explained over here, and suppose quantitatively when you have to perform any calculation, I mean to say if you see any kind of numerical problem, here you could see that you have a numerical problem. It's asking you if you dissolve a solute like camphor in ethanol, and it's 1.47 grams of camphor that is dissolved in 125 ml of ethanol, and density is provided. So how can you calculate the molarity and molality or molarity or the mole fraction? So again, so it is not a big deal when you have to calculate the molarity. Obviously now you have the mass of the solute, so that is 1.44 gram. So it's a 1.47 grams. You will be keeping it over here, and then you will be taking the formula mass, right? And volume, the total volume of the solution, obviously here it has been provided for ethanol, and that is not a problem. If you choose 125 ml as the volume of the solution, assuming that 1.47 gram is not going to significantly alter the volume, so therefore you can choose, but you have to choose here the L units, and therefore it's 125 L, right? and now when you are going to evaluate it, right, you will be having the correct value of the molality. In terms of molality, then in order to arrive at the mass, so you have been provided with the volume and the density. So therefore, what you will be doing, so density, it is mass over volume, right? So in order to calculate the mass, so density is in gram per ml, right? And volume is in ml. So therefore, you can cancel, and eventually you will come the grams, and you have to convert this grams into kilogram, and this kilogram must be over here. So by plugging the value of the kilogram, you will be able to calculate the molality. So I have already performed the calculation. We don't need to go through that. The only my purpose is that how we can apply these definitions to a real problem. Okay, so regarding the mole fraction, so I'll take another 2 minutes before I come to this slide. So mole fraction, you know that suppose if we are dealing with a kind of a solution. So solution is solute plus solvent. Okay, and if we consider it 100%, right, and you could have the percentage of the solute from anywhere between 1% to all the way 99%. Okay, so in that way the definition reverts as you are going to have more than 50% of the component, then that would be solvent and the other one would be solute. So solute and solvent is not strictly designated terms for the solid substance or the liquid substance. It's the general definition. Anything which is greater in amount, whether volume or the solid mass, so that will be the solvent. Anything that is in smaller amount should be the solute. So the thing is here, on the basis of the solute and the solvent, we have the definition or the term we call fraction. So fraction in fact is what we say that if the amount of the solute is 10%, we know that the amount of the solvent is 90%. So we will say that this is in part, and if I take the total amount of this, that is 100%, so I say whole, that is the definition of a fraction. Now we have to apply this general definition on the mole fraction. It means that instead of the percentage, if we deal with, I'm coming back here, if I take moles of solute plus moles of solvent, and then the same formula I'm going to apply. So therefore, if I have to calculate the fraction, but the question is for whose fraction I'm talking about. If I'm talking about the fraction, suppose if I'm saying that fraction is, sometimes the people use f, but the correct way to apply the fraction is x. X is, in most of the textbook, it is the x term, that x is used for the fraction. So if I say that mole fraction of solute is moles of solute divided by the total mole, or I can say the moles of solute plus solvent. So moles of solute plus moles of solvent. And I suppose if you have to calculate the moles of the solvent, so then instead of moles of solute, you will be using moles of solvent. So why I am explaining these basic terms, the reason is because at some point when you are preparing the solutions for the synthesis of nanomaterials, you need these terms, and you have to be very, very clear that how you are going to use them and what is the meaning of these terms and how, in which respect you will be applying it. After that, there is another important aspect in solutions. in what way we can explain the solution of nanomaterials in aqueous or a non-aqueous phase? Somebody can ask you that it is not that traditional kind of a solute which can be dissolved in a solvent. You know, the nanoparticles are crystalline when you are dealing with the gold nanoparticle or the magnetic nanoparticle, which I'll be explaining after some time. They are crystalline nanoparticle. So if somebody asks you that it is basically a heterogeneous phase. It is not a homogeneous phase because the solid particle is suspended in the solution. Yes, absolutely. Conceptually, it is correct that the nanoparticle which is suspended in the solution, so it is not entirely dissolved in the solution. But can we term the suspension of the nanoparticle a solution? Absolutely. Because the definition of the solution is that one where a solute which could be one or two is homogeneously dispersed throughout the bulk of the solution. That is the definition of the solution. So there it comes the term miscibility, immiscibility, insoluble, and the saturated solution. There is no issue with the sodium chloride, potassium chloride, sugar. You will be having a completely homogeneous solution. The miscibility is fine. There is no problem with the methanol, ethanol, and you will have a homogeneous solution from 0 to 100% mixing. But the problem arises when you have slightly a longer tail in the alcohol as you move from methanol, ethanol, propanol, butanol. So then it becomes the problem. It's not a complete miscibility. Miscibility term is being used when the components are entirely miscible, right from 0% to all the way to 100%, right? Immiscible, oil and water, where there is practically no possibility of the miscibility among the molecules. Insoluble, so you can say insoluble or miscibility. Actually, the term miscibility we use when we deal with the liquids. So insoluble when we deal with a solid, one component is solid, usually the solute, and the saturated is the saturated solution. This is very, very important. You have to keep in your mind that for the saturated solution, the term solubility, the definition of the solubility applies to the saturated solution, not to any concentration below that, right? So if somebody asks you that this is the solubility of sodium chloride in water, it means that he or she is referring to the fact that at this concentration, you are going to obtain a saturated solution at a particular temperature and pressure. So that is the meaning of the solubility. So anyway, coming back to our problem that actually I'm sorry, I'm running slightly fast because I have to cover so many slides. So coming back to the same question, should we call the nanoparticle solution a homogeneous solution or not? Absolutely, we can call, as long as you have the stable suspension and you have the constant value. Suppose for the gold nanoparticle, if your absorbance of the gold nanoparticle, the intensity, not the wavelength I'm saying, the wavelength of the absorbance of the gold nanoparticle is 520 nanometer. With the concentration, that wavelength is not going to change. But with the amount, the intensity of that absorbance is going to change, right? So therefore, what I want to say that as long as the intensity of that absorbance remains constant with the passage of time, the solution is homogeneous, and you can say that it is a solution where gold nanoparticles are entirely suspended, and that is the requirement for any kind of application of nanomaterials in the liquid phase, whether that is aqueous or a non-aqueous phase. So you must have a homogeneous solution. So when we will be dealing with the application at that time, I'll explain that why we need a completely homogeneous solution of nanomaterials. So this thing you already know. Here from propanol to all the way hexanol or beyond, if we keep on increasing the length of the hydrocarbon chain, right? So that is that reduces the solubility. Now, the question is that why it why it happens that the solubility of alcohol with the increase in the hydrocarbon chain that reduces because it has a direct relation with the solubility of the nanomaterial in the aqueous phase if you are dealing with the aqueous phase solution, right? So in the nanomaterials, it is not that straightforward the way we are going to explain it. This is very straightforward. Everybody learns this from the BSc, that why the higher alcohols are not soluble and miscible in the aqueous phase. But when we deal with this kind of solubility in for the nanomaterial, it becomes much more complicated. So I'll explain that, I think, in the next lecture. Okay, so what happens here? Suppose if I'm saying it is much easier to understand if I'm going to explain it in terms of salt. Suppose if I am dealing with ammonium chloride. Okay, this is ammonium chloride in water, right? And for the time being, you just forgot about chloride because the term which we are going to explain it over here, that has no relation with the chloride. It's a spectatrine and it's already soluble. So I have 4 hydrogen to make ammonium ion. If I replace one hydrogen, and by replacing one hydrogen, I add the hydrocarbon tail, right? When the ammonium ion is dissolved in water, it is completely soluble. There is no issue. But when I have to add some kind of hydrocarbon tail, now if somebody asks you, this is the Lewis structure of water. So this is the Lewis structure of water. 104 is the angle, right? And it's a dipole, partial negatively charged, partial positive charge, right? And we can simply depict it by this kind of a cap, right? So it means that this is electronegative end of the dipole and electropositive. On the basis of this, how you are going to arrange it? Obviously, you are going to arrange it like this. Or what I am saying that it is in fact a blanket of hydrogen bonded water structure around the cation, and I can say this is the hydration sphere of water. But the question is how I am going to draw the hydration sphere of water over here. This is a problem because here it is CH2, 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 obviously CH3 over here. Right. Now, so the thing is that this hydration sphere exists because of the ion-dipole interaction. But those ion-dipole interactions are not polar. This is entirely non-polar region. So there is a water structure breaking, the hydrogen bonding between the partial negative to partial positive end, partial negative to partial positive end, and partial negative to partial positive end. That when breaks, then the ion-solvent interaction come in effect, right? Ion-solvent interaction when the dipole molecules, so they have to solubilize a ion, dipole molecules of water, they need to break the hydrogen bonding, then only the ion-solvent interactions are going to be established. But the question is, how we are going to depict this? If I am going to depict it like this, right, now what should be the orientation of the water molecule? The orientation of the water molecule, suppose if I am saying like this, it is not like the proper order where the negative end is directed towards the positive end. That is not the case, but it's the orientation that helps to strengthen the hydrogen bonding. So here the hydrogen bonding is strengthened, right, and therefore the blanket of the hydrogen bonding which is created over here, that is much more stronger than the rest of the bulk of the water molecule, because the water molecule want to run away from the non-polar portion, right, polar portion, and they want to run away. But the problem is because this part holds the molecule in the bulk, whereas this part feels uncomfortable and wants to move away. And this kind of competing two kind of competing forces which will decide the fate of the molecule. Should it be in the bulk solubilized, or should it be expelled from the aqueous phase? As the hydrocarbon chain becomes more and more longer, it means that magnitude of the surface area of this, or the magnitude of the non-polar interaction, will exceed the polar interaction. Eventually, the non-polar interaction will push the molecule to the interface, and thereby insolubility arises. So that is the reason why as we keep on increasing the hydrocarbon tail, and why the molecule is becoming more and more insoluble. Now this has a direct relevance to the nanomaterial chemistry. So the question is, you don't have the hydrophobic or the hydrophilic environment in the nanomaterial because they are crystalline. So why some of the nanomaterials are completely water soluble, and why some of the nanomaterials are insoluble, that we will come when we deal with that part after a few lectures. So I here just wanted to establish the definition, right? And okay, before going ahead, so do not hesitate to ask me any question, right? So please go ahead. So I'll give you a minute, and if you have any question, you can ask me before I go ahead. Okay. Solubility of solvent, for the time being it is not that important, but I have included this slide to just explain, because we have different kinds of solid. So the crystalline solids, so they are not soluble in the aqueous phase. Now it's a very conflicting statement. So the nanomaterials are all crystalline solid. How we can say that? Then the nanomaterials are bulk soluble. So we will come to that part, and slowly. But for the time being, you just need to know that crystalline solid molecule here, diamond is crystalline, graphite is amorphous, right? And metals do not dissolve in water, and ionic solids. So most of the ionic solids are soluble, but there are several ionic salts which are not soluble. Now we come to the aqueous phase. You know the term sustainability. Suppose we have to apply the nanomaterials for the benefit of the humankind. The life survives in the aqueous phase. You see, we have the oceans of water, not methanol, ethanol, right? And likewise our human body, the biochemical reaction in the human body, so they take place in the aqueous phase. All biochemical reaction in biology, which we are going to study, so they need the aqueous phase, where obviously pH is the predominant condition in order to trigger those biochemical reactions. So it means that water is very important component for the nanomaterial application. So the kind of nanomaterial synthesis I will be explaining, so that synthesis we are going to conduct in the aqueous phase entirely. So the synthesis of iron oxide nanomaterial, as well as gold nanoparticles, silver nanoparticles, you will see most of the publications, they focus on in the aqueous phase. People do research in the non-aqueous phase, but most of the application of the nanomaterials, so they restrict to the aqueous phase. So we know that water is very important. So no doubt, from the biological point of view, it is the medium where life originates and sustained. It's a highly polar solvent and geometry. And one very important question. If somebody asks you that what is the Lewis structure of carbon dioxide, you know that it's a linear, and the bond angle is 180 degree, and here the bond angle is, you have seen, 104 degree, right? And there are 3 atoms in carbon dioxide, in water also there are three atoms. But what compels carbon dioxide not to have the liquid state or the condensed phase, and what compels the water molecule to have the condensed phase? In this environment, we have plenty of carbon dioxide, but it is all together in the gaseous phase. Your oceans, freshwater lakes, so all lot of water molecules, lakes, and you don't have any lake of carbon dioxide, right? So that is the uniqueness of the water, because despite having the much smaller size, just of three atoms arranged in a band structure, right? Just like that of a carbon dioxide. So this water molecule is extremely important, not only from the our survival point of view, sustainability point of view, but as a very good solvent. So this is all together because of the hydrogen bonding, because the hydrogen bonding which you see in water molecule, it is it doesn't exist in many of the molecules frequently available in our environment, which are having the three atom structure, right? So this hydrogen bonding keeps the water molecule in the condensed state, and that is the reason when we talk about the solubility. Solubility is the term when we apply it when there is reversibility between the solid solute, partitioning between the solid state to that of the saturated solution. So it means that if you keep on adding sodium chloride at a constant temperature in room and pressure, right, at some point you won't be able to dissolve any more amount of sodium chloride, that any added amount of sodium chloride will be settled down. So what is happening? It's not exactly the same crystal which are going to be settled down. It is exchange between the solution and the solid. The number of sodium chloride molecules which you are going to dissolve in water at the saturation point, it's saturated solution, exactly the same amount is going to be precipitated out. That is the definition of the solubility at constant temperature and pressure. Now, the best way is to understand any change in thermodynamics, you know that. So any change that is in terms of energetics. So you know the definition of enthalpy. So enthalpy is a very quantitative parameter that can right away helps us to understand if the heat is going to be consumed, if we are dealing with the heat energy. The heat is going to be consumed when a change is happening, or a heat is going to be released when a change is happening. So when it is consumed, it is endothermic. When it is released, it is exothermic. So we can also talk about the energetics of the nanomaterial, but the fundamental basis to understand the energetics, it's not just single step dissolution process of the energetics. It's a multi-step, as in the case of sodium chloride. When you add sodium chloride in water, in order to dissolve sodium chloride, first you have to break the crystal. Wherever you are going to add the energy, include the energy in any form, maybe a heat energy, right? So that is the endothermic process. The endothermic process means the enthalpy is positive. This is the y-axis, energy axis, you see over here. So it means that if I have to split the crystal into its constituting ions, right, and it means that I have to work against the lattice energy, that energy which holds the oppositely charged ions in the three-dimensional lattice. Okay, so that is the reason the delta H for the first step, did you see the first step? So that is positive. So if somebody asks you, if you are going to say somebody that when we dissolve sodium chloride, energy is released because it's an exothermic process. He or she may ask you, okay, I'm holding this water bottle, you add sodium chloride and you are saying energy is released, heat is released, I don't feel it, right? So it is the amount of energy that should be fair enough to be sensed by your touch senses. If the amount is too low, very small, you won't feel it, right? But when the energy is too high, obviously you see the warmth, right? But the question is, somebody can ask you, but you have to break the crystal. How you can see the energy is released? So then you have to come at this part, you have to explain this, that it's not just one-step process, it's a multi-step process. Energetics of a change, any change, whether physical or a chemical change, so it happens through multiple steps. And the final addition of all the steps will conclude if the change is endothermic or the exothermic. So how? The first step is endothermic. Now, as I told you that if I have to solubilize iron in the dipolar water medium, I have to break the hydrogen bonding. Again, because I am breaking the hydrogen bonding, I need to input the energy. Again, energy is required. So you see delta H2. Now, the length of the arrow, you see the length of the arrow? That corresponds to the amount of energy. So amount of energy that is consumed to break the crystal is much greater in comparison to amount of energy that requires to break the hydrogen bonding, right? But once you have broken the hydrogen bonding, right, now you see the water molecules are independently existing to solubilize the ion. So then, now you have independent ions ready to interact through the dipole ion type of interaction, okay? And this change, this step is highly exothermic. The energy is going to be released from here to all the way here. So what is the conclusion? The conclusion is that that's this solubilization of sodium chloride in water. If I have to calculate the delta H of solubilization, it means that I have delta H1, delta H2 and delta H3. Now, what the phase diagram is saying? The phase diagram is saying that delta H is plus and delta H2 is also plus. It's endothermic, right? That is endothermic, but delta H3 is negative. So it means that negative delta H3. Now, it means that it is in fact the competition between the two endothermic or the exothermic amount of the energy is consumed or released. But whatsoever is greater in amount, that would decide if the change is endothermic or positive, endothermic or exothermic. So here we know that when we dissolve sodium chloride in water and the resulting delta H of the solution is negative. So it means that this term delta H3 is more predominant than delta H plus delta H2. You got my point?
Yes.
So this is the way we decide the enthalpy of, if it is applicable to the physical change, it's a physical change, right? It's a physical change. The physical change, the definition of the physical change is that the molecule of the solute or the solvent, when they are going to mix together, they are not going to alter their actual geometry. So water molecule remains bent before the dissolution. Water molecule remains bent after the dissolution. Sodium chloride is sodium and the chloride ions in the lattice or in the dissolved state. So if I'm going to heat it, evaporate water, sodium chloride will revert back into the lattice structure. So that is why it's a physical change. But when the molecular structure of any of the component is going to alter, that is a chemical change. So I mean to say that, so when you are dealing with the energetics, so make sure that you know all the three steps. So this is simply the solubility with respect to temperature. So you don't need to deeply understand it. So anything potassium nitrate increases with temperature, all of them, only that of the lithium sulfate. Now we are coming to the colligative properties. So colligative properties, you know, are the properties of the solvents which alter when we add certain amount of solute in it. So it has a direct relevance to that of the nanomaterial solutions. So when the nanomaterial solutions are going to be prepared, when the nanoparticles are there in the aqueous phase, so are they going to affect the properties of the solvent or the medium where they are going to be suspended? Absolutely, the way this is the case over here. So Here we have the vapor pressure reduction, freezing point reduction, boiling point enhancement, and obviously osmotic pressure. So here I don't need to go through in any depth. So you see that when you are not adding the solute, the amount of the water molecule in the gaseous state that imposes the pressure by bombarding of the surface, that is known as the gaseous pressure of water molecule in the air just above the solution. But that gaseous pressure reduces when we add the solute. So it is, you see the yellow balls? So when we add the solute, the number of water molecules available to go up, that reduces and hence the vapor pressure of the solution decreases in comparison to that of the pure water. Mathematically, the mole fraction, I told you what is the meaning of the mole fraction over here, right? So the mole fraction of the solute decides how much amount of the gaseous pressure of the solution is. So greater the mole fraction, greater is the reduction in the gaseous pressure, because it's a fraction, you see, in the fraction amount. When you are multiplying any number with that of the fraction, the total value is going to fall, right? So that is the meaning for this. And here is, you can go through this because we are running out of time. So it's simple numerical problem. So you have the gaseous pressure of pure water, 4.4 kilopascal, and mole fraction you can calculate, multiply it, so that is the gaseous pressure of the solution. Boiling point, elevation. So we heat pure water. So what is the definition of the boiling point? The definition of the boiling point is when the gaseous pressure that is being produced over here, in more and more water molecules, when they reach above the solution, eventually they create the pressure that equalizes with that of the external pressure, that is 1 atmosphere, right? When that happens, that is the boiling point, and you see the bubbles coming out of the solution. But when you add the solute, the same thing happens as you see over here. So the solute restricts the displacement of water molecule to fly away in the air. The same thing happens. So therefore, the boiling point, in order to arrive at the boiling point, you need to heat more. That is why the boiling point elevation, right? And the freezing point, fall in the freezing point, obviously because you have the solute, so less amount of water is going into the solid state, and that is the depression in the freezing point. This is a very important phase diagram of water. Actually, I wanted to draw it, but I'm going to leave it. So the phase diagram, suppose if you are dealing with a solution at 1 atmosphere, when you increase the temperature, see over here, the temperature increases on the x-axis, and you keep the constant 1 atmosphere pressure as you have now in this room, right? And if you start with water that exists in the solid state, suppose if you see this is minus 20 degrees centigrade, obviously you are dealing with ice, you keep on increasing the temperature. Eventually what is happening, suppose if I'm coming over here, this is the melting point of water, right? So it means that this is 0 degrees centigrade, okay? And if I keep on further heating it, eventually this is the boiling point of water, that is the 100 degrees centigrade. So this line, just concentrate on this line for the time being. But when I'm performing the same experiment by adding certain amount of solute or the sodium chloride, so again I have the solid ice of the solution, sodium chloride and water at very low temperature. But you will see that the melting initially was helping over here, but now the melting requires much lower temperature, because at 0 degrees centigrade you won't see the formation of ice, right? So the formation of ice has been shifted to the lower temperature, that is the depression in the freezing point. And if I want to boil it, it is not boiling at 100 degrees centigrade. That was earlier I mentioned at this point. Now it is going to boil at a much higher temperature, that is the elevation in the boiling point. And likewise, this difference is the is the fall in the gaseous pressure. So I mean to say that, so hopefully I think this phase diagram is very popular and very common phase diagram, right? So you just try to understand that how temperature and pressure affect the aqueous solution, any kind of aqueous solution. So quantitatively you can provide the mathematical formulation delta F, that is the freezing point, depression, delta B, that is the boiling point, elevation. The formula remains the same, only the constant is going to change. Here you have the constant, freezing point constant, the value is already provided. This is the molality. Sometimes the molality term is being used as B, small b, so don't get confused what is the meaning of B. But now in modern IUPAC terminology, we use the term B. And I is the amount of ions produced. If you are dealing with sodium chloride, the value of I is 2, but if you are dealing with sugar solution, the value of I is 1. So we can apply quantitatively, calculate the freezing point, depression, or the elevation in the boiling point using the same formula for this solution. You have to calculate the molality. As I told you that you can calculate the molality by the mass of the solvent and calculating the moles. So you can calculate the moles by the amount of the solute provided, and you multiply the volume with that of the density. What is the density? Okay, it has been taken as 1. So density of the solution has been taken as 1. So it has been converted into kilogram over here, right? So, and by plugging the value for the constant, you will be able to calculate both the terms, delta F and delta F dF and F dV. Now the last one is the osmotic pressure. It's a very important term. So I'll take another 1 minute for this because it requires slightly. So for osmotic pressure, actually what is osmotic pressure? Osmosis, it is related to directly the osmosis. Osmosis is very common, the process which is commonly used in biology. So suppose if I have a beaker of water, right, and what I do, this is water, and what I do, I separate, I put the, what we call the semi-permeable membrane in that beaker of water, right, and here I have water molecules, right, and here also I have the water molecules, right, but in this side of the component, in the other side of the component, I add the solute. So obviously the amount of the water molecule which is available for the hydrogen bonding is much more over here than over here, because some of the water molecule is associated with the solute particle or the solute molecules. Therefore the effective amount of water reduces over here. So therefore water molecules start moving from the left component to the right component. Okay. Now this semi-permeable membrane only allows the water molecules to move, not the ions or the solute molecule, right? So if I place the lid over here, which is movable lid, right? So before adding the solute, the lid is at the same level in both the components. But when after a certain time solute water molecules move over here, this lid pushes to a greater volume. So you will see the volume of this side increases. Obviously, it decreases on this side, but the level of the lid, that is proportional to the external pressure. That is 1 atmosphere pressure. You may use, right? It means that in order to bring back to the same level of the lid, I need to add extra pressure. This extra pressure is in order to bring back this, so that the flow of water molecule from left to right can be can be stopped. This only can be stopped if I have the pressure equal on both sides. This extra pressure is given with the pi Greek letter, that is known as osmotic pressure, right? So now this is the osmotic pressure when I bring back the lid to the same level, and this extra pressure is proportional to the amount of solute. Only R is the gas constant, temperature is constant where you are performing the experiment. So it means the osmotic pressure is only related to the concentration. So the greater the amount of concentration over here you will be adding for the solute, the greater should be the osmotic pressure. So this is the main meaning for this, and you can also calculate the molar mass of the solute by rearranging the equation. So capital M is the molar mass. It is not the molar concentration, it is the formula mass, right? So this is the mass of the solute, gas constant, temperature, and osmotic pressure, and the volume. So here I have provided you just a minute. Yeah. Okay, so it is the last slide. So this is important, and you will have the direct relevance to the what we say material chemistry. How? You see over here, the question is asking you to calculate the formula mass of the solute. Aqueous solution contain 1 gram in 1 L of a derivative of detergent, sodium chloride NE1. Osmotic pressure of this solution at 25 degrees centigrade is provided this kilopascal. What is the molar mass of the solute, right? And you have already the equation which you have derived over here. You have the mass, that is 1 gram, gas constant you have substituted over here, temperature must be in Kelvin. You have to keep one thing in your mind, that whenever we are going to apply, you see you see the gas constant. The gas constant, though I need actually another lecture in order to completely define the definition of the gas constant, but in short, you should keep in your mind that gas constant, that is the constant for the ideal gas. Most of the cases we assume the non-ideal condition as the ideal condition, right? The gas constant helps us to convert the units to arrive at the required quantity, right? So without the gas constant, sometimes it becomes very complicated to arrive at the unit, but gas constant helps us to arrive at the units. You see over here, so therefore the gas constant is in Kelvin, is kilopascal per mole per Kelvin. So therefore, you are not supposed to use the temperature over here in degree centigrade. In this way, you won't be able to cancel the units, and you won't be having the appropriate units of osmotic pressure, right? You got my point. So therefore, when you have to deal with a numerical problem like this, you must pay your attention for the gas constant that is provided. Gas constant had different units for the different values, but you have to keep in your mind that which gas constant is provided in the numerical problem. If that is not provided, gas constant is required, so then you have to pick that gas constant which helps you to arrive at the required units. You got my point? This is very, very important. If the gas constant is provided, it's fine. If it's not provided, then how you have to choose? You have to choose that gas constant which can help you to cancel out the units, all other units which are not required, only the one that is poor. Okay, so here what we are going to do, the formula mass of the solute is 287. It is asking you to calculate the formula mass of the polar part. This is the molecular structure of the duodecyl alcohol, right? It means that this entire molecule has a formula mass 287. But you know that how much long is the hydrocarbon chain is C12. You know the formula mass for C12 is 155 gram per mole. You subtract from the value you calculated. This should be the formula mass of the polar portion, but this is very, very contradictory. Carbon is 12, hydrogen 1, oxygen is 16. If you add them, you won't get 132, right? So what is the problem? There is no problem with the calculation. Where is the problem? The problem is that here we are talking about the dry portion of the polar part. This is including the water molecule because the polar portion is also including the hydration shell. So therefore that includes the water molecule. Those are associated with the polar portion. So this is the last slide, so I should conclude it now. This slide, this lecture was required because the lecture which we will go through, they required this fundamental understanding. So therefore, I thought to include the fundamental lecture so that it would be easier for you to understand the rest of the lecture. So in conclusion, so what we have learned, the nature of solution, determinants of the solubility, so how much soluble is and what are the driving forces as I talked about over here. Then the characteristic properties of the aqueous solution, those are particularly the all these osmotic pressure, depression, freezing point, elevation in bond point. So they are the characteristic properties as well as the characteristic properties of the aqueous solution means where we talk about the solubilization, and the colligative properties where we talk about all other properties of the aqueous solution when solute is dissolved and how it is going to affect the solvent property. So hope you have understood all the slides. Sorry about that, I have to run through and I had to cover so many slides. But if you have any question, please go ahead. Okay, then actually we are again coming back to the next lecture at the same place. So after I think 10 minutes. Right? Thank you so much.